The electron shooter shoots one electron at a time through the double slits at the screen. Draw the pattern that the electrons make on the screen after a long period of time in which many electrons have been shot at the screen, but the electrons have been shot at the screen one at a time. Well, before I solve this, what did you all think about the Dr. Quantum video in the lecture outline videos?
So cool. So cool.
It's crazy, huh?
It is crazy. And I have a lot of questions about it.
Yes, me too. And hopefully I can answer some of them at least. So let's go ahead and tackle this problem, and then I would love to talk about your questions. So the electron shooter shoots one electron at a time through the double slits. Actually, so based on watching the video, what is going to happen on the screen over time? Can anybody tell me?
We're going to have the distributed lines with some that are canceled and some that are amplified.
You got it. Thank you. So we're going to have the what's called the interference pattern or the diffraction pattern. Which means that on the screen there will be alternating areas of light and dark. So something like this. Something like that is fine, or something that indicates that there's a difference and that it is a pattern. Okay, so let me walk through a little bit about why this is. So you're shooting electrons one at a time, and these are the double slits, by the way. So, and first off, in order for this to work, the slits have to be on the order of the wavelength of the electron. So the slit size, or the holes in this screen, so each slit has to be approximately on the order of the size of, so I'll put a squiggly equals for approximately, the size of the wavelength of the electron, and we will calculate that in a homework coming up. But what happens is that one electron goes through both slits. Well, and let me backtrack there. So rather than saying one electron goes through both slits, what I should say is that the probability the probabilities associated with an electron go through both slits.
Hey, Robert, can you guys just make sure that you guys get done with
the probabilities associated with an electron go through both slits. And in the video, what they showed was that maybe 50% of the probability of was for the electron going through one of them, and 50% of the probability was for the electron going through the other one. And that it's actually the probabilities that interfere to create the pattern. And I'll write that right here. The probabilities interfere. So even if you shoot one electron at a time, right? Because in the video they talk about, well, if you shoot a bunch of electrons through the slits at a time, then maybe the electrons can bump into each other. So then they shot one electron at a time and still got the interference pattern. And the only conclusion was that the probabilities interfere, the probabilities associated with an electron. And that is important because we will start talking about electrons as if they exist as probabilities, and they do. And so we will end up having orbits, or what we'll call orbitals, in which we talk about, we will define their shapes in terms of the probability of finding an electron 90% of the time. Okay. Now, one other thing I'd like to say, I think one other thing before I open it up to questions about this. Let me see, the probabilities interfere. I lost it for a second there. I know there's something else I wanted to say. Oh, yes. So we will also talk about how in quantum mechanics, you cannot know both the position and the velocity of a electron with 100% accuracy. We'll talk about the Heisenberg uncertainty principle and how it relates to that. And we talked about that in the lecture outline as well. So what allows 50% of the probability to go through each slit is that we're not exactly sure where the electron goes. It's not like a baseball in which, for a baseball, where you throw it and you know where its position and velocity is at one time, you can predict its future position and velocity. One of the basic elements of quantum mechanics is that there's a limit as to how well you can know, how accurately you can know the position and wavelength or velocity of an electron. And that gives rise to why we have to talk about them in terms of probabilities, because we are not 100% sure where they are going to be once they leave the electron shooter until they hit the screen. So there is a probability field between once it leaves the electron shooter and once it hits the screen that says we don't know where the electron went. And then finally in the video, once they actually observed which slit the electron went through, it wasn't probabilities anymore. We knew it, and the probability field collapsed and the interference pattern disappeared. And I know that was weird in the video because they just worked up this giant eye. And so that was, that was not actually how you do it. They don't have giant eyes that can see electrons, but you can actually use a laser to tell which slit it went through. And once you use a laser, the interference or diffraction pattern collapses. Again, because once you know exactly what happens, there's 100% probability of where it is, and there's no interference of probabilities anymore. Anyway, I think that's all I wanted to say about this so far. Any questions you'd like to ask? I'd be happy to do my best to answer them, although it is a pretty crazy topic, but it's very interesting, I think.
Professor?
Yeah, Daryl?
Yeah, talking about the video, where they moved the giant eye, or as you said, laser to observe it. And you said you're going to know which slit it went through. Why does that affect the fact that it no longer has the interference on the screen?
Okay, so good question. Let me see if I can do my best to answer it. All right, so this interference pattern occurs because there's a 50% probability, let's say, and to set up this experiment so that's exactly 50% for each of them is a hard thing to do, but let's imagine that we could. So, and so again, we know where the electron is when it comes out of the shooter. We have no idea where it is in here exactly. I mean, we have an idea, we have some idea, but there's 50% and 50% probability. And it is the probabilities that interfere. and make the diffraction pattern, okay? So then we go to a place where, and I shouldn't have used red for that, but so now let's do a double slit experiment, and I'll do this down here, where we have two slits and a screen and an electron shooter. And now we observe that the electron goes through this slit. And once we observe it, we know, so there's 100% probability that it goes through one of the slit, and there's 0% probability that it goes through the upper slit, let's say. And for that reason, there's no, so if there's 0 probability here, that means that there's no chance, there's nothing for the other probability field to interfere with. So it's like here we have two waves, right? Because an electron has wave-like properties going through each slit, 50% of the probability. Here it's like we have one wave going here and no wave, 0% probability going through the other one. So there's nothing to interfere or nothing to diffract, no wave. So let me see that. No wave. Right? Because the key element is if you're going to get interference, you need something to go through each of these slits. And I think that's my first attempt at answering that question. I don't know if that works, Daryl.
I understand the 100% probability and the 0% probability, but my problem is you knowing the 100% probability and 0%. How does that affect the screen?
So this one down here would act as if only something went through this slit, and so there'd only be a little mark right there.
So
yeah, but
Daryl, go ahead, and then I'll take Selden's question.
Oh, okay. Why is it the case that when we observe this, when we're not observing, we see interference or a diffraction pattern, but when we're observing, we don't see a diffraction pattern?
Yeah, no. So this is the one that we observed. I mean, I think. So, okay, so I've got a couple not perfect analogies here, but let's try this analogy and see. So let's say you played the lottery, okay? And you bought one ticket. Now, until they make the drawing, so let's again, I don't know how this is going to work. It works sometimes. It works okay. So you're playing the lottery. And you buy one ticket. Okay? Now, but the drawing hasn't happened yet. Let me ask you this question. Have you won the lottery or have you lost the lottery when you've bought a ticket before the drawing? Or can't you tell?
You can't tell.
You can't tell, but there is a probability that you've won, and there's a probability that you've lost. Are you okay with that statement?
Yes.
Good. Okay. And those two probabilities are coexisting. So in theory, where we come back to the electron is that if those probabilities coexist, then in theory they could interfere with each other and cause diffraction on the screen. Okay? But then they have the drawing. And the two probabilities, what we could call probability fields, right? I mean, I guess as the drawing goes, right? And maybe you get the first three numbers, and so the probability field changes a little bit, and it looks like you might win. But then the fourth number and the fifth number come up, and they're not your numbers, right? And so as the drawing occurs, the probability fields collapse. And they collapse because you have observed what the answer is. And that's what happens to the electron. The probability fields collapse when you observe it. And then there's no interference between the possible electron going through one of the slits and the electron going through the other slit. So observing things collapses the probability field.
Does it matter what side of the double slits that you observe?
Good question. So no, it doesn't. Right. Okay. So let's say you observe the other position, right? And you shoot an electron.
Like on the back side or the front side. So like watching it either come in or go out of the double slit. Does it matter which way you look at it?
It does not matter.
So if I had a laser on the back side, it wouldn't matter. Like I know that it came out of the left slit, even though like it could have come in during the right one. Wouldn't you be able to observe some of the like atom going through on both sides? I feel like, how does observing cause it to change? That, I guess that blows my mind.
Exactly. That's my question too.
Yes. How does observing cause the behavior to change? All right. And again, so let me write that down and let's tackle that. Okay.
Like, does my observing cause...
Sorry, Sheldon?
Oh, you're good.
I didn't hear the end of yours.
Oh. That's basically what I'm asking is how do you keep it from collapsing? Is there a way to keep the probability from collapsing? That'd be my other question.
Oh, yeah. Well, so the only way to keep it from collapsing is to not observe it. So,
okay.
And so just like the only way to not know, to keep the probability fields for the lottery experiment is to not have the drawing.
Mm-hmm.
Right? So once you observe an event, all of the probabilities collapse because, so you can think of, and again, I don't know if this is going to work either, but so my daughter and I have been watching some of the Marvel shows where they talk about the multiverse. And so basically every time you make a decision, all of the probabilities for the other events, like some people would say they collapse and they don't exist anymore. And people who are working on the multiverse theory would say that they go to other universes. But basically, whenever you make a decision, if you had more than one choice, then like
it'd
that,
be another string, yeah.
Yeah, and so, but as long as you don't make the decision, then you have all these probabilities of what could happen. But
Professor, there's a really similar thought experiment close to this. It's called Schrodinger's cat.
Yes, I'm familiar with it. Do you know enough to talk about it?
I know simply like you just put a cat inside a box with a radioactive material and you can't guess whether or not it's alive until you look at the box.
Right. So yeah, no, this is definitely a thought experiment. Do not try this at home. But you put a cat and there's 4 legs and whiskers, so that becomes a cat. And then, so the way the experiment goes, as far as I remember it, is inside there's a little ledge and there's a radioactive isotope. And you wait until there's exactly a 50% chance or probability, to come back to our 50% probabilities from the electrons. there's a 50% probability exactly of the radioactive isotope decaying and either breaking a bottle of poison or whatever, but of killing the cat. But there's also, since we don't know, this is a black box, we cannot see inside, or let's say 50% probability that the cat is dead. And there's a 50% probability that the cat is alive. And it's not a perfect thought experiment, but if you imagine what quantum mechanics would say is that until you observe the cat exists as two equal probabilities, and therefore we don't know what the answer is. And so these two probabilities overlap until we observe. And you might say, well, what about the cat? The cat's observing, but that part doesn't play into the experiment. Josiah, is that what you remember about this, the Schrodinger's cat?
Yeah, close to it, yeah.
There's a umlaut over that, Schrodinger's cat. Yeah, but I mean, I think when I think of quantum mechanics and its relationships to these, it's definitely a work in progress for me as far as thinking about these things. And as someone with an engineering background, there's a level of an acceptance too, so I can work with the results, and especially these days when they're talking about quantum computers and overlapping states storing energy. So it's interesting because quantum properties are actually finally becoming important in everyday life. There are quantum corrections also to, I believe, GPS systems. Because in Newton's time, way back in the day, when an apple fell on his head and he developed, classical physics, everything was so small that this kind of thing didn't matter. Electrons were not even known to exist back then. But anyway, but now things are getting smaller and smaller, and electron properties do matter. Let's see if I can back out a little bit there. There we go. And let me see if I can summarize. So first off, this only matters for electrons in a chemistry class. If you're in a physics class, then anything electron size or smaller, this would matter for. Then second, for electrons, they're small enough that their wave-like properties matter. And again, we'll explore that in upcoming homework. And then, what comes out of quantum mechanics is that there's a limit to how well you can know the velocity and the position of an electron. And that leads to these probabilities going through different slits being able to interfere with themselves. Like if you were to do this experiment with an atom of hydrogen, which is about 2,000 times bigger, and I think the atom of hydrogen is another one of the homework questions. If you do this experiment with an atom shooter of any kind, you will never observe this effect, because an atom is big enough that it acts the same as if you were throwing a baseball at this, right? The differences in, let's say this, the wavelength becomes so tiny that it acts just like a particle. I think I'm bringing in stuff that may be more confusing now. I'm going to stick to electrons. So electrons, so let me summarize again. So it is the probabilities that interfere when you shoot one electron at a time. If there are no probabilities, meaning that there's 0 and 100%, regardless of whether you observe where the electron went or you observe where the electron didn't go, if you say it didn't go here, then it must have gone here in this experiment. It collapses the probabilities. It collapses the diffraction or interference pattern. Anyway, let's see. Irvin, how would the pattern change if helium atoms? Yes. So, yeah, and the helium atom might be actually instead of hydrogen, but anything bigger than an electron, you will not observe this effect. And when we do the calculation later, we will see that it is the electron's properties of being approximately 2,000 times smaller than a proton, which means it's about 2,000 times smaller than a hydrogen atom, that allow this to experimentally be measured. For a hydrogen atom, for a helium atom, anything bigger, you cannot observe these effects because they're too tiny. They're there, but we can't observe them. So anyway, we'll do some calculations for that coming up on future homework questions. So Irvin, I hope that answered your question. How about anybody? Daryl, Selden? It might be time to just sit with it for a few minutes, but let me see if there's one more question. Anybody?
Professor,
Yes, Daryl?
you did mention in chemistry we're sticking to electrons, right?
Yes.
Because
Electrons and bigger.
electrons are bigger.
Yes.
Okay. Out of chemistry, what do we have that are smaller than electrons? I know about just the nucleus, quarks, I don't know. And in quantum computing, they talk about superposition of bits, the probability of a bit being 0 and 1 at the same time. Is a bit smaller than an electron?
Okay. So first off, let me, the first question, an electron. So in chemistry, there's nothing smaller than an electron that we typically care about. I mean, like anything, once you get to getting your PhD in it, people are interested even in smaller parts and their effect on chemistry, but that's graduate level work. So anything in undergraduate level, and even my graduate work and most people's, the electron is the smallest thing that you have to worry about. And you're right, in physics, there are quarks, there are muons, gluons, things that I, frankly, are something that I haven't thought about in a long time, and it would take me a while to refamiliarize myself with them, some of which I've never gotten. And then, sorry, in that answer, I forgot about the second part of your question, Daryl.
Oh, I was just comparing like the quantum mechanics we're doing now to the quantum computing I've been hearing so much about, talking about superposition of bits, the probability of a bit being 0 and 1 at the same time. So
yes,
does that mean if we observe it, it disappears too? I don't know.
Yes. So I don't know very much about this other than, so this principle where it's 50% going through one slit and 50% going through the other is the principle of superposition, because it means superposition of states. And something that I don't understand is how they can use the superposition of probabilities of an electron to store information, right? So that's something that is beyond what I know currently. It's very interesting to me. I mean, the only thing I can say is if you have, and again, bear with me, but so if you have two states, and just like you have two slits, and if the electron goes through one of them, or let's say this, if now there's three probabilities, there's like a bit is either a 0 or a 1. This could be let's call it the lower slit would be one state, the upper slit would be a second state, and the superposition of these two states, if you didn't know which state it was in, would be a third state. And so my uneducated in this area guess is that if you have a bit that has 3 states instead of 2, then potentially you can store a lot more information like exponentially more so. But how you monitor what state it's in, bottom, top, or 50% probability, I am very interested to know, but I don't know. So anyway, it's a great question. And so this is a good point. And Daryl and everybody, if there's a topic that we come across that you are interested in doing your own extra credit paper on, and again, it's just a page and a half, double spaced and typed, something like this, where you can do a little bit of internet research and type something up. I'm happy to work with you to do this, right? The whole point of extra credit is you do it, and it's because it's something that interests you. And because extra credit for me is like you have 2 5-point assignments to learn something beyond just what's in this class, or relate it to something in real life, or or related to quantum mechanics. So anyway, I'm happy to talk more about it. I'm happy to do a little research myself too, but it's just something I don't know about, which there's plenty of. So anyway, these are great questions. I think it's been over an hour. It's been a little longer than it usually is before we take a break. Is there any last questions before we take about a 10-minute break? This has been a great discussion, by the way, and I really appreciate it. All right, I'm gonna take a break. It's 1:40. Actually, I can stop recording that.